So from here, we can really start to get into some of the basics of what organic chemistry is, sort of how it's organized. So much of what's here corresponds to chapter 11 in the Smith text. But ultimately we're going to cover three major topics in this chapter. Again, two of which are covered in great detail here, one of which is, again, a review topic. So we're going to start with writing structures. As we alluded to during the Lewis structure review, when it comes to organic molecules, we can't really draw them in the same way that we do for general chemistry structures. And that's because organic molecules just build up complexity too quickly. And so if you start looking at a drawing that has 100 atoms in it, it really becomes difficult, even for someone with experience, to discern what's important in that structure. And so we're going to kind of redefine the way that we draw molecules. Acids and bases play a critical role in a lot of things we do in organic chemistry, and so we're going to spend some time reviewing that. If you need more time to review acids and bases, this is actually covered in chapter 9 in the Smith text. Or alternatively, if you still have access to your book from Foundations, you could refer to the material there. And then finally, we'll talk about functional groups. Functional groups are how we organize molecules. And so we'll talk more about that when we get there. But for now, what we'd really like to start with is to discuss how we write organic molecules. Again, why is this its own topic? Don't we already know how to draw out molecules with all the bonds? The answer is we do, and we've learned that in our Foundations course. But again, these molecules get too complicated too quickly. If you think about the molecules that you looked at, that we discussed, that we drew in Foundations, they were just a couple atoms usually. Maybe as many as 10 atoms sometimes. Well, if we start thinking about even simple organic molecules, for example, alanine. This is a molecule that's important in this class. It'll become important to you when you get to biochemistry, because this is one of our 20 naturally occurring amino acids. Structure for alanine, if we do it in the same way that we've done Lewis structures, looks like this. And this is one of the simpler amino acids. The full chemical formula for this, C3H7NO2. So again, this is a very simple amino acid, and it already has 13 atoms in it. If we get to more complicated amino acids or proteins, just start to think about how many atoms are contained in those molecules. And so we need a simpler way to represent this that still relays all of the information we have, but doesn't require this time-consuming drawing, and also helps us to better see what we're looking at. So again, I want to remind you of our general rules that we talked about in one of the previous videos, but again, they're important here. Carbon, 4 valence electrons. Needs 4 more, it forms 4 bonds. Nitrogen has 5 valence electrons, needs 3 more, and so ends up with 3 bonds and 1 lone pair. Now, these are what apply for when the atom is neutral. If we have an ion, cation or an anion, these numbers can change. But if we have a neutral molecule, then these are the numbers that we will pretty much always see. Oxygen, 6 valence electrons, forms 2 bonds, and has 2 lone pairs. Halogens all have 7 valence electrons, and typically 1 bond and 3 lone pairs. Now you may remember you saw other examples in foundations where a halogen had an extended octet and therefore extra electrons. Yes, those things happen, but we actually don't see a lot of that in organic chemistry. So for the most part, when we deal with halogens here, it's 1 bond and 3 lone pairs. And finally, hydrogen has 1 valence electron, but because its nearest noble gas is helium, it just forms 1 bond. So let's start looking at some molecules. Let's go to propane. So propane, C3H8. Again, this is a relatively simple organic molecule. In fact, this is an extremely simple organic molecule, just 11 total atoms. And yet look at how long it takes us to draw it. And again, this is a very simple molecule. It only has 3 carbons. Think back to a complicated molecule. Previously, I've talked about Taxol. How many atoms does Taxol have? Taxol's formula, C47H51NO14. And so if we have to sit here and draw out every one of those 113 atoms, we're going to be here for a while. So when we draw organic molecules, we're going to do it in one of 2 ways. We have what's known as a condensed structure. This still shows all the atoms, but it does make the way we draw it a little bit simpler. And so what it does is we would start with 1 carbon at a time. So this first carbon, the one on the left, you can see has 3 hydrogens bonded to it. So we would write that as CH3. What's on the next carbon? The next carbon has 2 hydrogens. So we write it as CH2. And that last carbon has 3 hydrogens, so we would say CH3. So we can see already with the condensed formula that things are a little bit simpler. We still have all of the information available, but we didn't have to draw out every single bond, so a little bit easier to write. And we do use condensed structures pretty regularly, but the most common thing that we use are what are called line structures. And the line structure for propane looks like this. So the question you might ask is, well, where did all the atoms go? So let's look at this structure more carefully. Here's propane again as a line structure. And the reason that line structures work is because of something we've already said a number of times in this class. And we'll keep saying this on a regular basis. Carbon forms 4 bonds. Always, always. If carbon didn't form 4 bonds, or could change the number of bonds it formed, then line structures wouldn't work at all. We wouldn't be able to use them. So how does this work? Well, every vertex is a carbon. So what do we mean by a vertex? We mean anywhere that a line ends, such as this position, or this one. Or we could also mean any spot where 2 lines come together. And so with the 3 spots I've highlighted, you can now see that we've got a total of 3 carbons. So the carbons are still there. They're just assumed there. But where did the hydrogens go? Well, that's when we again have to come back to this key point. So if we look at this first carbon, how many bonds does this carbon have? We can see very clearly that it's bonded to one other carbon. But if carbon has to have 4 bonds, then where are the other 3 bonds? Well, that's where we make this very important assumption. Any bonds not shown are to hydrogen. So what does that tell us? That tells us that this carbon is bonded to 3 hydrogens. Again, let's review what we meant by that. So with that carbon, we can see that it's very clearly bonded to one other carbon, that one here. Since carbon has to have 4 total bonds, and we only see one of them, that means the carbon, we can assume it's bonded to 3 hydrogens. What about the atom in the middle, the one I've highlighted in blue? Well, we can see it has 1 bond to carbon, 2 bonds to carbon. So it's bonded to 2 carbons. Again, we need to have 4 total bonds. So to get to 4, then that tells us that there's 2 bonds to hydrogens. So that's what we see with the carbons and hydrogens now. In fact, we don't even have to draw them in. We just know that they're there based on the drawing. What about atoms other than carbon and hydrogen? What do we do with those? So here's ethanol, for example. So the carbons, we do what we did on the previous page. We just draw the line in. So this carbon is this carbon, and it's bonded to this carbon. But our green carbon is also bonded to an OH group. So what do we do with that? We just draw it in. So all non-hydrogens, non-carbons are drawn in. So you never have to figure out whether there's a nitrogen or oxygen or halogen or sulfur. It's just going to be there. And the same thing is true for nitrogen. Finally, all hydrogens on non-carbons are drawn in. So if you have a hydrogen that's on an oxygen, you have to draw that in as well. So now you should look at the exercise on line structures, and we'll come back and solve those in a few minutes.